Dear children, today we are going to study about the telescope. You know that telescope. It is an optical device which enables us to see distant objects clearly. There are different types of telescopes. They are refracting telescopes and reflecting telescopes. Refracting telescopes make use of lenses to see distant objects. Reflecting telescope make use of converging mirrors to view the distant objects. There are two types of refracting telescope. They are astronomical telescope and terrestrial telescope. Astronomical telescope is used to see heavenly objects like sun, stars, planets, etc. Terrestrial telescope is used to see distant objects on the surface of the earth. Similarly, there are different types of reflecting telescopes are there. They are Newtonian telescope and Cassegrain telescope. First, we want to study about the astronomical telescope. So, you know that it is used to see heavenly objects like stars, planets, satellites, etc. In astronomical telescope, there are two lenses are used. One is the objective and the second one is the eyepiece. Objective is a convex lens of large focal length and a much large aperture. It faces the distant objects. In order to form the bright image of the distant objects, the aperture of the objective is taken large. So, one question this one, why the aperture of the objective is taken as large? What is the answer? In order to form the bright image of the distant objects, so that it can gather sufficient light from the distant objects. Then second one, eyepiece. Convex lens of small focal length and a small aperture, that is known as the eyepiece. It faces the eye. The aperture of the eyepiece is taken small so that whole light of the eyepiece may enter the eye for distinct vision. Okay. Like in the compound microscope, here also there are two cases. The first case, final image is formed at the least distance of distinct vision. So you want to find out the magnifying power in this case. So what is the magnifying power? It is defined as the angle subtended at the eye by the final image formed at the least distance of distinct vision, that is D, to the angle subtended at the eye by the object at infinity when seen directly. So this is the magnifying power. So we can write the formula, that is m equal to beta by alpha. So beta is the angle subtended at the eye by the final image and alpha is the angle subtended at the eye by the object. Okay. Now we can see the first case, final image is formed at the least distance of distinct vision. So this is the objective and this is the eyepiece. Objective has large aperture and the eyepiece has small aperture. So here the object is at infinity. In the case of telescope, we should place the object at infinity. So we can note here, this is the objective. Okay, this is the object, that is at infinity. So from the object, the rays directly falls on the objective. So one ray passes through the optic center directly. Okay, one ray passes through the optic center directly. And another one ray after refraction passes, and these two rays meet at a point where the image is formed, that is the focus of the eyepiece. So here the object is at infinity, so the image is formed at focus of the objective. Okay, focus of the objective, that we can note it as A dash B dash. So the object is at infinity, then the image is formed at the focus of the objective. So this is the optic center. Then this image acts as a object for the eyepiece, and this image is in between the focus of the eyepiece and the optic center of the eyepiece. Then this image acts as a object for the eyepiece. Then after refraction, the final image is formed. Okay, after refraction, we can note the arrows here, also arrows. Okay, then after the refraction, so here the one ray passes through the focus of the eyepiece and the other one ray passes through the that is optic center of the eyepiece. Then after refraction, the final image is formed at the least distance of distinct vision from the eye. Okay, final image is formed at the least distance of distinct vision from the eyepiece. So this is the final image. Clear? Okay, this is the final image and it is formed at the least distance or distinct division from the eyepiece. That is from the eye. We can see the image from here. And this is the focal length of the objective. Okay, this is the focal length of the objective and this is the focal length of the eyepiece. Okay, focal length of the eyepiece, and this is the image distance of the eyepiece. Sorry, this is the object distance for the eyepiece. That is the UE. This is the object distance for the eyepiece. Clear? So once again, the object is at infinity. Then first image is formed at the focus of the objective, and this image acts as an object for the eyepiece, and final image is formed at the least distance of distinct division from the eye. Then we can find out the magnifying power. So you know that magnifying power is the ratio of angle subtended by the image to the angle subtended by the object. That is, angle subtended at the eye by the final image formed at the least distance or distinct division to the angle subtended at the eye by the object when that is at infinity. That we can write m equal to beta by alpha. So what is beta and alpha from the figure? So here alpha is the angle with the object. So here the object is at infinity and the rays directly fall through the eye like this. Okay, from the infinity the rays directly fall here. So this is the angle with the object. That means this is the angle between the object and the eye. So we can note it as alpha. So this angle and this angle is similar because alternate angles. So we can note this as alpha. Clear? And what is beta? So here the image is formed here and the rays from the, that means from the image the rays fall to the eye. Okay, so this is the rays to the eye from the image. So what is the image angle? Okay, image with the eye. So this is the angle. Okay, this is the beta. Okay, beta is the angle subtended at the eye. Okay, that means with the image to the eye. That is the beta. Clear? So from this alpha and beta, we can find out the magnifying power. So from the figure, we can note that A dash O B dash. Okay, A dash O B dash, that we can note it as alpha, angle A dash O B dash, that is equal to alpha. Then angle A double dash E B double dash, that is the beta. Okay, so we can write angle A double dash. Okay, A double dash E B dash, A double dash E B double dash, that is equal to beta. Okay, so that is the alpha and beta. So what is the magnifying power? It is the beta by alpha. So for small angles, we can write beta is approximately equal to tan beta and alpha is approximately equal to tan alpha. So we can write tan beta and tan alpha from the figure. So what is the tan beta? So these two angles are similar angles. Okay, these two angles. So A dash E B dash and A dash E B dash. So these two angles are similar angles. So we can take this angle. So what is the tan beta? That is the A dash B dash divided by B dash E. So we can write A dash B dash divided by B dash E divided by what is alpha? Tan alpha. Okay. Tan alpha from this figure, from this triangle. What is the tan alpha? A dash B dash divided by O B dash. Okay. So we can write A dash B dash divided by O B dash. Clear? So A dash and B dash we can cancel. Okay, A dash and B dash, A dash B dash we can cancel. So what is remaining? This comes to the numerator. So O B dash divided by B dash E. Okay. So what is the OB dash from the figure? OB dash. Okay. OB dash. So this is the B dash. Okay. So what is the OB dash? It is the focal length of the objective. So that we can note it as FO divided by what is the B dash E? This is the B dash E. What is the B dash E? It is the object distance for the eyepiece. So with the negative sign we can write minus UE. So this is the general formula for the magnification of the astronomical telescope. M equal to F0 by minus UE. Okay. Then we can find out this 1 by UE. So we can take the lens formula. We can substitute apply the lens formula for the eyepiece. So what is the lens formula? 1 by V. Okay. 1 by V minus 1 by U equal to 1 by F. So we can apply this for the eyepiece. So for the eyepiece, what is the object? That means object distance U, that is U equal to, from the figure, U equal to UE with the sign convention minus UE. Then what is the image distance for the eyepiece? That is the D with the sign convention minus D. Image is formed at the least distance, a distinct division. Then we can substitute here. That is 1 by minus D minus 1 by minus UE, that is equal to 1 by F. F is the focal length of the eyepiece. Okay, so we are taking the this formula, we are applying this formula for the eyepiece. So F equal to FE. So from this equation, minus into minus plus. So that is 1 by UE equal to 1 by FE plus 1 by D. Okay. Then we can take the 1 by FE outside. So what is remaining? That is 1 plus FE by D. Clear? Then we can substitute this 1 by E in the above equation, M equal to minus F0 by UE. So we can write M equal to, okay, M equal to minus F0 into 1 by UE. Oh, what is 1 by UE? This value, 1 by UE. So we can write minus F0 by FE into 1 plus FE by D. Okay, so this is the magnification or the magnifying power of an astronomical telescope when the final image is formed at the least distance of distinct division. Clear? Now we can see the second case of the astronomical telescope, that is the final image is formed at infinity, that is the normal adjustment position. So here also we can place the object at infinity. Okay, object is placed at infinity. So from the infinity, that means from the distant object, one ray passes through the optic center. Okay, one ray passes through the optic center, that is undeviated, and another one ray after refraction passes through the objective, and these two rays meet at the focus of the objective because the rays are passing from the infinity. So the image is formed at the focus of the objective. This image acts as an object for the eyepiece. So this image also falls on the focus of the eyepiece. Then only we get the final image at infinity. So here also after the refraction, okay, that is the focus of the eyepiece, and another one ray passes through the optic center of the eyepiece. Then final image is formed at infinity. Okay, final image is formed at infinity. Clear? So here the object is at infinity, so image is formed at the focus of the objective, and this image acts as an object for the eyepiece, and the final image is formed at infinity. Okay, so the object of the eyepiece is placed at the focus of the eyepiece, then only we get the final image at infinity. Then we can find out the magnification, that is the magnifying power, m equal to beta by alpha. So what is the beta and alpha in the figure? That is as in the same case. So this is the alpha, that is the angle between the object with the eye. So this angle is also alpha. So what is the beta? That is the angle between the image with the eye. So this angle is the beta. Then we can note the image, that is the A dash B dash, and this is the optic center of the objective, that is, so this is the optic center of the eyepiece, that we can note it as E. Then we can find out the magnifying power, m equal to beta by alpha. For small angles, beta is approximately equal to tan beta and alpha is approximately equal to tan alpha. So we can write tan beta and tan alpha from the figure. So what is the tan beta? You take this triangle. So what is the tan beta? A dash B dash divided by B dash E. So we can write A dash B dash divided by B dash E. Then divided by, what is the alpha? Tan alpha, you take this triangle, that is the A dash B dash divided by OB dash. Okay, so we can write A dash B dash divided by OB dash. Then the A dash B dash will cancel, then we can write OB dash divided by B dash E. So what is the OB dash from the figure? OB dash is the focal length of the objective, so we can note it as F4. Then what is the B dash E? B dash is the focal length of the eyepiece, that is the FE, that is equal to the object distance for the eyepiece. So we can note it with the sign convention, that is the minus FE. So we can write the minus here. Okay, that is m equal to minus F0 by FE. So this is the magnifying power of the astronomical telescope when the final image is at infinity, and this is the case for the normal adjustment. Clear? Next type of telescope, that is the second category of telescope, that is the reflecting telescope. Here you want to study about the Cassegrain reflecting telescope. So the figure shows the Cassegrain reflecting telescope. So in this type of telescope we are used the mirrors, concave mirror. Okay. So this is the diagrammatic representation, ray diagram for the Cassegrain telescope. So it consists of a large concave mirror, that is the paraboloidal mirror, and it acts as an objective having a hole at its center, and there is a small convex mirror. Okay, this is the small convex mirror and it is known as the secondary mirror. Okay, this is the convex mirror, so we can shade here, and it is the that is the secondary mirror, and this is the concave mirror and we can shade here. This is the concave mirror. Clear? And this is the large concave mirror with a hole at its center. It is known as the paraboloidal mirror, or it acts as an objective. And the second one, that is the small convex mirror, that is the secondary mirror near the focus of the primary mirror. Okay, it is placed near the focus of the primary mirror. The eyepiece is placed on the axis of the telescope near the hole of the primary mirror. Then the parallel rays from distant object are reflected by large concave mirror, and before these rays come to focus at F, they are reflected by the small convex mirror and converged to a point I, okay, just outside the hole. Then the final image formed at I is viewed through the eyepiece. Then the first image F is inverted with respect to the distant object. Second image I is erect with respect to the first image F. Okay. Hence, the final image is inverted with respect to the object. So, this is the working principle of Cassegrain reflecting telescope. And we can find out the magnification or magnifying power when the final image at D, that is m equal to f0 by fe into 1 plus fe by d, and when the final image is at infinity, m equal to f0 by fe equal to, for the objective we can put r by 2. So, m equal to r by 2 divided by fe. Okay. What are the advantages of reflecting type telescope than the refracting telescope? So first point, a concave mirror of large aperture. We are using a concave mirror of large aperture, and it has high gathering power and it absorbs very less amount of light than the lenses of large apertures. So the final image formed in reflecting telescope is very bright. So even very distant or faint stars can be easily viewed. Okay, that is the first advantage. Second advantage, due to large aperture of the mirror, the reflecting telescope have high resolving power. Okay, that is, so we get the very bright image. Then the third point, as the objective is a mirror, it is free from chromatic aberration. So what is the chromatic aberration? It is the formation of colored image of a white object. So here the objective is a mirror. So it is free from chromatic aberration. Okay. There is no formation of colored image of a white object. Clear? The fourth point, the use of paraboloidal mirror reduces the spherical aberration. So what is the spherical aberration? Formation of non-point blurred image. Okay, non-point blurred image of a point object. So here when you use the paraboloidal mirror, it reduces the spherical aberration, that is the formation of non-point and blurred image. It is not formed. Okay, the non-point and blurred image is not formed when you use the paraboloidal mirror. Okay. Then what is the fifth point? The cost for constructing reflecting telescope is much less than the refracting telescope, because here in the case of reflecting telescope we are using the mirror. So mirror requires grinding and polishing of one surface only. So it costs much less to construct. The last point, a lens of large aperture tends to be very heavy, but a mirror of equivalent optical quality is weightless. Okay, so here a lens of large aperture, it should be very heavy, so it is difficult to make and support by its edges. But when you use a mirror of equivalent optical quality, it should be weightless and can be supported over its entire back surface. Clear?